Welcome to NPTEL course, a basic course on electric and magnetic circuits. In this lecture on DC circuits, we will discuss on Thevenin theorem and its application. This is a very useful technique for the network solution. It provides a way to replace a part of the circuit by an equivalent circuit. The key point here is it provides a way to replace a part of the circuit by an equivalent circuit. So, it provides an equivalent circuit of the part of the circuit which you like to address. So, like a linear two terminal circuits connected to a load at terminal A B, then you can get the corresponding Thevenin's equivalent at A B terminal. So, the theorem states that a linear two terminal circuit. So, linear circuit we have already defined. A linear two terminal circuit can be replaced by an equivalent circuit consisting of a voltage source VTH in series with a resistance RTH, consisting of a voltage source VTH having voltage VTH and in series with a resistance RTH, where VTH is the open circuit voltage at the terminals. We know open circuit and short circuit, where VTH is the open circuit voltage at the terminals and RTH is the equivalent resistance at the terminal when the independent sources are turned off. When independent sources are turned off. So, two things we have VTH, the open circuit voltage. So, we know this open circuit condition we will see, and then we have RTH, the series resistance, equivalent series resistance. How to obtain this? Is the equivalent resistance terminals when independent sources are turned off. So, turn off means, as we have already done in case of superposition, turn off means voltage source shorted, V equals to 0 and current source open. So, that I equals to 0. So, all the for RTH finding we will make all the voltage sources to be shorted and all the current sources to be open, and then we will find the RTH. So, at that time no source will be there in the circuit. So, with this again I am reading, a linear two terminal circuit can be replaced by an equivalent circuit consisting of a voltage source VTH in series with a resistance RTH, where VTH is the open circuit voltage at the terminals and RTH is the equivalent resistance at the terminals when the independent sources are turned off. So, if this is the circuit and you like to corresponding equivalence of this portion from A to B left hand side, and this is your load say resistance and so, then the equivalence will look like this as per the Thevenin's theorem. VTH open circuit voltage and RTH the equivalent resistance seen from the terminal A and B. So, the circuit becomes this, then the analysis of the circuit becomes this source, this resistance and the load whichever you are concerned of. Then the corresponding current through the resistance or whatever element is there across the AB, it becomes pretty straightforward. Now, we will verify Thevenin's theorem in the laboratory through an experimental setup. A simple experimental setup is shown as in the diagram. So, it has a voltage source R1 and R2 are two resistances connected as shown, and then we have this AB terminal on which to the left hand side we will see find the corresponding Thevenin's equivalent, and the right hand side we have connected a load resistance RL, this we call the load resistance RL. Now, we will verify the corresponding Thevenin's theorem the way we have studied through this different calculation process and so. For this our objective is to that for this circuit we will verify the corresponding Thevenin's theorem. So, we will find the corresponding VTH and RTH for this at the terminals A and B, and then add the corresponding RL and you find the corresponding current. So, the calculated current and the experimental current through an ammeter will verify and then check that the corresponding Thevenin's theorem holds good. So, the VTH is open circuit voltage across AB terminal. So, you open the corresponding RL and check what is the corresponding VTH value. calculate IL from the given RL connected, because RTH also will find, and then from the RTH and VTH we will find the corresponding IL value for a given RL value, and then check through the experimental setup that what is the corresponding actual IL also through the ammeter reading also, and then compare the corresponding calculated IL and the corresponding measured IL. Now, we will verify the Thevenin's theorem in our experimental setup. For this, we have the arrangement. So, if you see here, we have the corresponding voltage source here, which is supplying to the resistance R1, R2, and the corresponding to the RL to the load resistance. So, this R1 and R2 are connected, and the RL across which we have the corresponding AB terminal in the description of the circuit, and from which we will apply the corresponding Thevenin's theorem from the AB terminals, and we will find out the VTH and RTH for there, and then based on the value of the RL, we will verify the corresponding current to the RL. Now, from the experimental setup, it is connected now. We see that the corresponding voltage across the load resistance RL happens to be 3.588 volt, and the current through the corresponding load resistance RL happens to be 0.072 ampere. So, from there you can find out the corresponding RL value. Now, note that for this corresponding RL value in this arrangement for this R1 and R2 resistances, the current happens to be IL equals to 0.072 ampere. So, this is the major current to this RL. So, from this setup right now we got the value of the RL value from the voltage and current, and also the major current to this RL value. This will be useful for our verification purpose. Now, in the next step, we will go for the measurement of the V Thevenin's voltage in the setup. So, for that we will open the corresponding RL value, the current to the RL. So, that is why this becomes the open circuit condition for this one, and at that time the corresponding VTH value happens to be 9.22 volt. That is the Thevenin's, the corresponding open circuit voltage for the purpose. Now, in the next stage, we will go for the corresponding RTH value, which will be using in the calculation process using the corresponding RL value obtained from VL and RL. Now, we will get the RTH value, the Thevenin's resistance value for the circuit. For that, what we have done, that we have sorted the source side, and then we have from the AB terminals, we will measure the corresponding resistance value of the circuitry, and this is the RTH value from the multimeter directly we are getting, and the value obtained happens to be 77.4 ohm. So, the RTH value for the corresponding circuit from the AB terminal and with the source sorted, we get the corresponding value to be 77.4 ohm. This will be useful for our verification calculation. Now, to verify the Thevenin's theorem for another RL condition, VTH, RTH remaining same, that will mean to say that R1 and R2 remaining same and the VS same. So, we will change the corresponding load resistance now, load resistance RL for a different set of RL value, the corresponding, we have switched on the circuit. So, the corresponding VL value happens to be 5.196 volt, and the IL measured happens to be 0.05 ampere. So, from this we can find out this RL value and theoretically calculate the corresponding IL value, and we will compare with the corresponding measure IL value for this purpose. So, we obtain the two cases for this verification using the corresponding VTH and RTH for the circuitry at the AB terminals, and we will see that from the observation table that the Thevenin's theorem holds good. As mentioned in the laboratory experimental setup, after taking the observations, we have tabulated the corresponding data in a table, and then we have two cases, case 1 and case 2 for two different load resistances. So, what we say is that for case 1, the corresponding VTH and RTH already obtained is 9.22 volt open circuit voltage at AB terminal, and the corresponding RTH is 77.4 ohm, and the corresponding RL value from the VL and IL measurement we got it to be 49.833 ohm for the first case, and then thereby we get the corresponding measured value also through the ammeter reading to be 0.072 ampere, and the calculated value as you calculate in the different calculations in our earlier discussions, that the calculated value of IL is VTH upon RTH plus RL. So, we know this VTH, we know the RTH, and now we have the RL value already there 49.833. Substituting those value of VTH, RTH and RL, we got the corresponding value of this calculated current to be 0.072 ampere. So, the corresponding IL value calculated is 0.027 ampere and also the measured value is 0.072 ampere. So, exactly we are getting the two values same. It implies that the Thevenin's approach which we have studied is also valid for the experimental setup also. Case 2 is with the different value of RL. So, here the corresponding RL value is 103.92 obtained from the voltage and current reading, and the VTH and RTH remaining same. Now, the calculated value of the corresponding IL value happens to be 0.05 ampere, whereas the measured value happens to be also 0.05 ampere as measured through the corresponding ammeter in this experimental setup. So, we found that for both the cases the Thevenin's theorem is found to be in agreement with the what we have studied. We will see how we can apply the Thevenin's theorem and learn the technique for circuit analysis. So, let us we have a circuit like this. So, the question asks is that find the I x in the 24 ohm resistance. So, find the corresponding I x downward in the 24 ohm resistance. So, this is a circuit. So, as per the Thevenin's things, the corresponding circuit becomes equals to A to B will have a VTH and RTH equivalent circuit to the left of AB, and then the corresponding load, the load is nothing but the 24 ohm resistance in this case. This will be 24 ohm resistance in this case. So, the circuit becomes pretty simplified, and then you can find the corresponding current through this band is VTH upon 24 plus RTH. So, that is the corresponding current, and then you can find. So, the VTH is nothing but the open circuit voltage at the terminals. Open circuit means we will open the corresponding 24 ohm here and find the corresponding VTH. So, that VTH becomes equals to VAB with 24 ohm being open. RTH is the equivalent resistance at the terminals when the independent sources are turned off. So, what does it mean? So, RTH when you look from this AB terminal AB, so then the resistances are 2 ohm, this is 12 ohm connected to the B side, and then we have 6 ohm here, 6 ohm here, and then the corresponding source being shorted, turn off. So, now we look into the corresponding RTH, this becomes your RTH. So, RTH equals to 2 in series with 6 and 12 are in parallel. So, that becomes the corresponding RTH value for this case, and VTH becomes equals to what? The VTH becomes equals to in this case the open circuit voltage. So, for open circuit voltage this is your 10 volt, 6 ohm, 12 ohm, and then we have 2 ohm, and this is our terminal AB which will be kept open. 24 ohm resistance is kept open now. So, at this time we will find out this VTH. So, VTH equals to VAB. Now, we see here what is VAB here? No current is flowing to this 2 ohm. So, this voltage across here, let us say CD will be same as the VAB. So, what is the corresponding voltage VCD here now? Because no current is flowing in the 2 ohm, neither there is current from D to B also. So, VCD is how much? VCD equals to VAB equals to VTH, but this in this case the corresponding current is flowing like this only in this path. So, this becomes equals to the VCD becomes equals to nothing but 10 minus 6 ohm into the current is nothing but 10 divided by 18. 10 divided by 18 is the corresponding current, and the voltage drop here is in the 6 ohm across this. So, that becomes nothing but the corresponding VC with respect to the D. So, that is nothing but the corresponding voltage. So, we got the corresponding VTH like this. So, we will see this Thevenin resistance RTH for this circuit as you narrated comes out to be this with RTH AB from AB. So, this becomes 2, 12, 6. So, that gives you 2 plus 6 in 12, and that gives you the 6 ohm resistance. So, this is about RTH we obtained for as per the Thevenin's equivalent circuit seen from the terminal A B. So, what we are doing here from terminal A B we are looking to this Thevenin's equivalent, and the Thevenin's equivalent of this terminal becomes equals to, as you say, the voltage source V t h with a series resistance R t h. So, this is nothing but your A B terminal now. So, the equivalent of from to the left of the A B terminal, all the whatever circuitry is there, that comes out to be a voltage source and a series resistance source, and then you connect the corresponding 24 ohm resistance, then you can find the corresponding current through this one. Then we will find the corresponding V t h now. In case of V t h, we will keep it the open, and then this circuit becomes this. So, V t h, as I already mentioned, V t h equals to V a b, that equals to 12 into 10 by 18, that becomes equals to 20 by 3 volt. So, this voltage drop across 12 is also same thing, current through this is nothing but 10 by 18. So, that becomes equals to 20 by 3 volt. So, we got the both R t h 6 ohm, V t h 12 by 3 volt. So, the circuit becomes now 12 by 3 volt source, R t h is 6 ohm, in series with the corresponding 24. So, this I x to this 24 ohm becomes equals to 20 by 3 divided by 20 plus 6 equals to 30. So, that becomes equals to 2 by 9 ampere downward, 2 by 9 ampere downward. So, that is the answer for this circuit, and this is also true, as you see here the corresponding circuit is like this 10, 6, this. So, at this point the corresponding 12 and 6 are in parallel, 12 and the corresponding 6, these are parallel. So, that becomes equals to 12 and 26 are in parallel. So, that becomes equals to 19 by 27 ampere, this I t total, and I t is shared between 12 and 26. So, I x in this branch 12 become equals to 2 by 9 ampere. So, already in our earlier discussions from Thevenin's theorem approach also we got the I x to be equals to 2 by 9 ampere from the V t h and R t h. So, simple parallel circuit analysis also reveals 2 by 9 ampere, and our Thevenin approach also reveals 2 by 9 ampere. So, by this way we verified that by solving this network by Thevenin's approach we can get the correct answer also. But this is a simple circuit, we will see more complex situation also. Next example, find I x in the 10 ohm resistance. Find I x in the 10 ohm resistance. Now, we have multiple sources, 5 volt voltage source and both current source. So, two things we will do first, R t h from terminal A B. So, we are looking at the R t h now 5 ohm, and the sources will be off. So, current source should be off means open, voltage source should be short, B equals to 0. So, that is the situation. So, R t h becomes equals to 5 plus 5 10 ohm, straightforward. Now, V t h, what you do is that we keep open the corresponding 10 ohm now. So, we will find the V a b here. So, this V t h equals to V a b equals to V c d. So, no current flows through this 5 ohm resistance. So, we will find the voltage across the V c d. So, that is the 1 ampere current source. So, what we see here 1 ampere current is flowing like this, is bound to flow. So, the voltage at C with respect to D is 5 volt, this is plus minus, this is plus minus, voltage rise. So, 5 volt plus 1 ampere into 5 plus 5, that becomes equals to 10 volt, So, this is about 10 volt across B c d, that equals to V a b. So, V t h becomes equals to 10 volt. So, now we see that the corresponding equivalent circuit for from terminal A B becomes equals to V t h 10 volt, R t h 10 ohm, and then we connect the corresponding 10 ohm resistance to find the corresponding I x. So, the I x become equals to 10 volt divided by the 10 plus 10 20. So, 0.5 ampere downward. This is how we solve the network issue current through any branch by find the equivalent of the Thevenin's equivalent first to the rest of the network, and then we add that particular component and then solve the corresponding questions. Next example, little bit more complex. So, you see here this is the circuit and the question actually find the I x in the 40 ohm resistance. So, I x marked like this, find I x from B to D in this circuit, and the circuit is provided with 2 volt source. So, as I mentioned, we will first find out this R t h and then we will go for the then V t h. So, we will find the corresponding equivalent Thevenin's equivalent across the terminal. What are the terminal? The terminal is nothing but the D and the corresponding point B. So, across the terminal D B 40 ohm is there, but we like to connect the have the corresponding equivalent across B and D, the corresponding V t h and R t h, and then we will connect the corresponding 40 ohm and find the corresponding I x value there. So, how to proceed for that? First R t h. What is R t h? R t h is that looking from the terminal B and D and making the sources off. The source here is 2 volt which is connected between A and C. So, off means it is a voltage source. So, it will be shorted. So, that becomes B equals to 0, that is the condition. So, therefore, A and C are shorted. So, this becomes A and C, they become the same point now, and then we are looking from this A and B, the B and D terminal. So, this is the B and D terminal and the A and C collapse. So, therefore, this A and C becomes same point, and then we have B to A is 10 and A to D is 20, D to C and A are same. So, that equals to another 15, and then B to C and B to C to A are same. So, this is 30. So, the circuit becomes from B and D terminals 20 and 15 in parallel in series with 10 and 30 in parallel. So, that results in R t h equals to R d V equals to 15 into 20 upon 35 and 15 into 30 upon 40. So, this is the condition 20 in parallel with 15 and then plus 30 in parallel with 10. So, this is about that R t h between B and D. So, we got this R t h from this, that comes out to be 16.07 ohm. Next we talk about the V t h. For V t h we see that we will remove the corresponding 40 ohm resistance and just keep it open. So, we will find the corresponding open circuit voltage at V t h, that is nothing but the corresponding V t h equals to here V b minus V d, I am assuming that B to be positive, higher potential than the D, it may or may not in the answer. So, V b minus V d. So, I will find out that now I will find out, let us say C is your reference. With respect to C I will find B potential V b, and with respect to C reference C I will find V d. How? If we apply this in this keeping it open, which simplify the problem. So, now this case the corresponding current will flow like this and another current will flow like this. Let us say this is I 1 and this is I 2. So, 2 by 10 plus 30 is 40, 2 by 40 is I 1 and 2 by 35 is I 2. So, we know that. So, therefore, across 30 ohm this is nothing but the corresponding 2 ampere 2 divided by 40 is there. So, 30 into 2 divided by 40 is nothing but the corresponding voltage at V b, and similarly the corresponding current through this I 2 is nothing but 2 upon 35. So, what you do is that the voltage D V d becomes equals to 15 into 2 upon 35. So, this is about the V d, and similarly you got the V c V b. So, now V b minus V d gives you 0.643 volt, 0.634 volt. So, we got this V t h. So, therefore, the equivalent circuit diagram from terminal B d with V t h becomes equals to 0.643 and R t h in the earlier slide you found it to be 16.07. So, this is B to D. So, this is about the Thevenin's equivalent, and now we connect the corresponding 40 ohm which is there in between B and D, and find the corresponding I x, from B to D. So, that leads to the corresponding current to be 0.643 divided by 16.07 plus the 40 ohm. So, this is the current which flows from B to D as per the circuitry here. So, that is the answer for this case. The current comes out to be positive, that is 0.0115 ampere, and therefore, the current is flowing from B to D. Now, we will go to another example, where we will strike a different situation. The question is, they find the voltage across the 1 ampere source. Find the voltage across the 1 ampere source. So, this is not a resistance now. Then there may be a curiosity to you that can you remove any source now, because in this case if you like to find out this corresponding Thevenin's approach, apply the Thevenin approach, then you have to open this VAB. So, here we are not opening a resistance. Can you open a current source or voltage source, whatever is there in between A and B? The answer is yes. So, this is a simple case. So, what we say that here this is AB. So, we remove the corresponding 1 ampere, and then we will find out this corresponding RTH now. So, that becomes equals to 5 ohm here, and towards this side also 5 ohm, and this is 10 ohm, and then we will go close this, and towards this side is nothing but voltage source. So, for RTH this will be shorted. So, across this AB terminal we will find the corresponding resistance RTH. So, this becomes equals to 5 in parallel with 5 plus 10 15. So, this is RTH, and when we go for this VTH. So, for VTH what we do here? For VTH we keep the corresponding AB terminal open circuit voltage. So, then this becomes equals to your 5 ohm, this is 5 volt, and then this side is 5 ohm and 10, 5 and 10. So, now you find the corresponding AB terminal voltage. So, this is driving the current. So, the driving current is this, and the voltage across the 10 plus 5 15. So, this becomes equals to 15 into the current is 5 upon 20. So, this is the corresponding VAB voltage, this is equals to VTH. So, we got VTH, we got VAB. Now, with this VTH and VAB equivalent circuit, we can connect the 1 ampere and find the corresponding voltage there. So, we see this approach. So, now before going to that, I will check whether my approach is okay or not. For that, let us say I am applying the nodal method for the circuitry to find out the corresponding VAB, that is a voltage across the current source. So, here if I go by the nodal method, then at this node, this is one node only. So, I can say that the corresponding VAB. So, 1 ampere is entering positive, VAB I am taking this is a VAB, VAB minus 5 by 5, this is negative, current going like this way, VAB upon 15 minus VAB upon 15, that equals to 0. So, the nodal equation KCL we apply, and then this gives us the VAB to be 7.5 volt. Now, with Thevenin's things, this for the same circuit which we already discussed. So, we got this RTH as we drew here with open circuit 5 this. So, this gives to be 3.75 ohm, 5 ohm in parallel with 15 ohm, 3.75 ohm, and VTH here 5 and 5 this 10 are connected. So, we find the VAB. So, this gives also the corresponding VTH to be equals to 3.75 ohm. Now, the Thevenin's equivalent across AB for this circuit after removing the current source, that becomes equals to 3.75 VTH and 3.75 ohm also RTH, and then we connect the corresponding current source now AB as in the diagram shown in the problem given, statement from circuit given. So, this 1 ampere is going upward. Now, for this case the question asks is that find VAB, that is voltage across the corresponding current source. So, voltage across the corresponding current source. So, 1 ampere is flowing like this. So, this is this. So, this is negative, this is positive. So, this corresponding this is positive, this is negative as current is flowing from right to left. So, rise in voltage. So, 3.75 the plus in conclusion, we see that the corresponding voltage across the current source happens to be 7.5 volt. So, theoretically using the nodal method also we find it to be 7.5 volt and verify that through Thevenin's approach also this corresponding voltage is 7.5 volts. So, it implies that we can apply the Thevenin's equivalent by replacing the corresponding current source also, resistance, voltage source, whatever is the corresponding element here. So, in conclusion that we see here the Thevenin's theorem and we can apply it to different circuits for finding the currents, voltage across an element, a resistance, current source and so. Thank you.